Hey everyone, this is Cameron Price and Mitchell Fisher presenting our automated lunar lander game. This is our final project for Chemical Engineering 436, taught by Dr. John Hedengren at BYU.
Our primary objective was to implement PID controllers, one in the vertical direction and one in the horizontal direction, in order to successfully land the lunar lander in the game. We decided to, as a secondary objective, to optimize the PID tuning parameters in order to minimize fuel consumption and still successfully land.
This is how the game works. This is the lunar lander, and there are three thrusters. There's one in the right direction, one in the left direction, and one in the vertical direction. Which means for the horizontal PID controller, the value can be anywhere from negative 100% to positive 100%, with negative referring to the left and positive referring to the right. The vertical thruster can have a value of anywhere from 0 to 100%, and the goal is to take this lander to the landing zone and impact the landing zone at a speed below 30 here.
So this is the model that governs a lander that might be landing on the moon. So for the vertical direction, the acceleration is given by these terms. This is the acceleration from the thrusters, and this U sub V is the fraction thruster. So this is the percent thruster, but it's between 0 and 1 times the acceleration from the thruster. And this G is obviously the acceleration due to gravity, which is propelling it towards the moon. So then if you integrate that with respect to time, you get this expression for the vertical velocity. The horizontal velocity is the same thing. It's just a little bit simpler because there's no gravity. The velocity is the integral with respect to time of the acceleration from the horizontal thruster multiplied by UH, which is percent thruster in the horizontal direction between -1 and 1.
Now we're going to present the open loop control. So this is no PID control, just me controlling it. So I'm going to start by powering on my vertical thrusters. Since it's manually controlled, I can only have 0 or 100%. I can't do any analog control. I'm also controlling the horizontal thrusters at the same time, but they just aren't a feature. They aren't shown on this program here.
Nice. Are you gonna do it?
Looks like this might work. All right, so my vertical speed.
You ran out of fuel.
I ran out of fuel, but I got under speed, so we're good.
Very nice.
So our goal, right, is to do this landing and not run out of fuel, and perhaps have a more continuous approach rather than on-off control.
The first thing that we did to get some PID tuning parameters was to model our process using a step response test. The physics of the game are completely made up because it's a game, so we thought it'd be easier to do a step test. So this is the vertical thrusters. As you can see, the gain is negative because the positive direction is defined as down towards the moon. So we have a negative gain. Once we were able to obtain those FOPDT parameters, we use those to get some initial PID tuning parameters. And then we were able to just manually kind of tweak those and tune them ourselves to get a controller that actually worked and landed the lander successfully every time. But that was not necessarily optimum for fuel consumption. So then we went ahead and iterated on those to find the optimum tuning parameters for fuel consumption.
And we acquired those optimal parameters by performing a sensitivity analysis. As you can see, we have these two graphs here, vertical position versus time and horizontal position versus time. And we simply took our base case that we had found just by manually tuning, and we tried different combinations or different multipliers on all of those base cases. And what we found was that the orange line here got us there the fastest without crashing. These two cases here that got up there a little faster actually crashed. And we found that those parameters used for this orange line were consistent in landing the lander.
And they also minimize the fuel consumption.
Yeah. For the horizontal position versus time, we found that actually this grouping right here of three, they minimized fuel consumption the most, but they didn't always land the landers. So we ultimately decided to go with some parameters from this grouping that minimize fuel consumption while also landing the lander in every instance. Here are the parameters we used. Ultimately, we made the integral term 0 because offset isn't a concern in this system. And now we'll present the results of the controller on the system. So this is the closed loop demonstration. As you can see, the horizontal thrusters already fired, and now we'll wait. This is the aggressive vertical model, and so it fires the last possible second, and you can see the vertical speed got just under 30 right before landing. And that was kind of one of the most extreme cases it could come across because the landing zone was so low. This one you see, once again, the vertical speed was below 30. And if you watch the fuel consumption as well, you'll find that we use significantly less fuel than we were in the open loop system. It's a great landing.
Overall, we found that the most optimal controller for the vertical thruster is pretty aggressive. It waited until the last second to burn the thrusters in order to save as much fuel as possible. We actually found that the horizontal thruster was a lot less aggressive, more conservative than we had initially anticipated. We needed it to be aggressive enough to avoid the terrain and get over the mountains, but if it's too aggressive, then it has overshoot and then it oscillates and becomes unstable. As far as real-world application, this is probably a little too aggressive on the landing because we would probably be more concerned about astronaut safety or the safety of the equipment, but this is a best-case scenario for fuel consumption, and we can always make it a little more conservative for safety after that.
And we'd also like to give credit to Rex Allison for writing the Lunar Lander starter code that we built off of. And thank you for watching.